morning. Thanks everyone for coming here for the last day one more time, and I'll let you guys go. I missed the first half of the game yesterday because I had a meeting here with Professor Dreyer, and when I came in to take charge, it was already too late. Where's the Italian guy? Congratulations. Oh, he's here. I thought you would be partying. Okay. So that was too bad. Anyways, let's get back to the not so fun things in life, although yesterday that wasn't fun either. So we were talking about the Levitt model, and we were talking about Levitt model in the context of modeling turbulent premixed flames. And before that, we discussed the different regimes that you have in turbulent combustion. And we identified essentially, let's say, 3 different regimes that we need to distinguish. Number 1 was a regime where the entire flame is thin compared with the smaller scales of the turbulence. That was the regime where the Corvalis number is smaller than 1. And in that regime then, because the length scales of the flame are small compared to the even smaller scales of the turbulence sees the flame as a discontinuity. And so in that respect, we can treat the flame as a discontinuity. And we call this the corrugated flamelet regime because the turbulence can corrugate the flame surface in that regime, but cannot enter the flame structure and destroy or mix up the flame structure. So in that sense, the flame retains a laminar flame structure. That was number 1. And then we said above a Corvalis number of 1, that would then be above a Corvalis number of 1, the turbulent length scales get smaller and can penetrate into get smaller than the flame thickness and can penetrate into the preheat region, and they cause turbulent mixing then in the preheat region. And in that regime then, and so we identified this regime as the thin reaction zones regime, and we said in that regime the turbulence is smaller than the flame thickness, but it's still larger than the reaction zone thickness, which is thin compared to the flame thickness. And then in that regime, the turbulence mixes, causes turbulent transport in the preheat zone, but but the turbulent preheat zone is chemically inert anyways. But we said it cannot, the turbulence cannot penetrate into the reaction zone because that is now thin. That reaction zone now appears as a discontinuity, or basically as a surface to the turbulence, and that layer then, the reaction zone, that retains a laminar structure. Okay, and then we said if you increase the Corvalis number even more, we identified a Corvalis number. So the Corvalis number can be written as, the Corvalis number itself can be written as the flame thickness over the Kolmogorov scale squared. And then we said we can also build a Corvalis number not with the Kolmogorov, not with the flame thickness, but with the reaction zone thickness. And then we used that Corvalis delta. We used that as a criterion for when the turbulence then also enters into the reaction zone. And when it enters into the reaction zone, the whole concept of, laminar flamelets or laminar flames, that should be out the window. Okay? And we said, well, that regime, we call this the broken reaction zones regime then, that regime, that might exist, but flames are prone to blow off in that regime. So maybe in technical applications, you don't find this that often. Okay. And then we said, okay, let's now we have different physics. Essentially, we have 2 different regimes where we want to describe flame propagation. That is the corrugated and the thin reaction zones regime. And we derived these equations in the two different regimes. So number one, the corrugated flamelet regime is this lower equation here. Here we have a propagation term, and then we had two different terms that come into this equation because they are modifications to the laminar burning velocity. And the first one here by curvature, and the second one by strain. And we looked at how large these corrections are, and we found, they are not zero. They're not, very small compared to this first one, but they were not too large either. There were corrections in the order of 20% or so, or less. And so that is just observed at this point. And then we derived an equation here for the level set equation for the thin reaction zones regime. And in that regime, then, we found there are two terms that appear. One is a propagation term with a burning velocity, and the other one here, a curvature term. And we said, first of all, we said this is a level set equation, so it tracks an interface, or it tracks a surface. And we said we want to identify that surface with the an iso surface of the temperature at the inner layer temperature. Okay, and then that surface travels with this propagation speed here, and we said there's one contribution here that comes from chemical reaction and normal diffusion in the temperature equation. And then there was a second contribution here, which was due to curvature in the temperature equation. And then we said, well, this here is not exactly the laminar burning velocity, but now, for the sake of modeling, we want to assume it is the same order of magnitude, or maybe it is the same. And then we can identify this SL, S here with SL naught, which is a quantity, that we know from measurements. Okay, so the big differences between these two equations, and we mentioned this also, are, let's say, this burning velocity here, but we say it's not all that different. And then the other one here is this diffusivity, because this is the real diffusion coefficient. This would be lambda over Cp, because this was derived from the temperature equation. So this is the diffusivity of energy, and then thermal energy, and then here we have the Markstein diffusion, which depends on the Markstein length, and is a different quantity. And then also we have this strain term here, which doesn't appear in this equation. Okay, so now if you want to compare this was derived from the temperature equation. And we could compare it now again with the temperature equation, and you see here the first two terms, they look very similar, especially if you add a density, if you multiply density into this equation. The first two terms look very, very similar, and what you see here is there's no diffusion term, the diffusion term, and there's no reaction term. But again, we said we can split this up into a normal and a curvature component. The curvature component is here, the normal component and the reaction component again. And so the diffusion and reaction, they're replaced by this propagation term in the level set equation. And one thing that is really important to note is that, let's see if that, is mentioned here explicitly. These level set equations, they are formulated for a surface. Okay, so in that sense, they are valid for the propagation. They're valid to tell you the position of a surface. For the corrugated flamelet regime, that would be the entire flame. For the thin reaction zones regime, that would be where the surface, isosurface of T equal to T naught is. So what this means is these are only valid, to describe the surface. They're not valid. They don't tell you anything else in the rest of the field. Okay? You need to define a value of G somewhere else, but it has not real physical meaning. Or at least even if you define a physical meaning to it, if you say it's a distance function, that equation wouldn't even preserve that. Okay? So these are only valid at the flame front. And then this here, of course, is a field equation, and it's valid in the entire field. Okay, so that's a big difference between these. Okay, so this is then how this looks like. Just as an example here, a little sketch. In the thin reaction zones regime, the flame is broadened by turbulence, but the reaction zone is still thin compared to the turbulent scales, and it appears as an interface. And the level set here only describes the location of this reaction zone. This is how this looks like. I showed you this DNS here before. And then look at the thick black line here. You know, I drew this in this picture, so it's not perfect, but that's kind of what the G, that's all the G equation would be. Okay, and all the rest you have to come up, you know, by other means. Okay, so now, next thing we want to do is we want to derive an equation, or now we have two equations, one valid in this regime and one valid in the other regime. And so we want to, you know, find one equation that's valid in both regimes. And so we start out with these two equations, and then, or let's start out with the second equation here. And then we non-dimensionalize this equation. And because all the action now that we're interested in between these two regimes, happen at the Kolmogorov scale. We look again at this diagram. It kind of looked like this: prime over SL, L over LF, and then here was the Reynolds equal 1 line. And then there was a line like this. This was Corvalis equal 1. And then there was a line like this somehow, and this was Corvalis delta equal 1. This here we call the, so this is where LF is equal to eta, and this here is where delta is equal to eta. And so this here we call the Klimov-Williams criterion, and this here we call the Peters criterion. So now so this is, right, is also, this then would be the corrugated flamelet regime, and this would be the thin reaction zone regime, and this here is broken reaction zone. So here we're not valid anyways, and so we want to look at, you know, how these equations in these two regimes come together, and that, you know, for that distinction, the Kolmogorov scale is very important. And so that's why we non-dimensionalize this whole thing here now with the Kolmogorov time scale and length scale and velocity scale. Okay? If we do that, we get an equation like this, where now, on that scale, all these star quantities, all star terms here, they're all order 1. Okay? And then here you get a d over nu. And if we assume unity Schmidt number or Schmidt number 0.7, whatever, then this is also order 1. And so you see this whole term is order 1. All this is order 1. The only parameter that really appears in that equation still is this ratio, SL divided by V eta. Okay? So now we can look at what is V eta over SL. And turns out, we said this earlier, the Corvalis number is really defined as the flame time divided by the Kolmogorov time, and that can be written like this by introducing here just the definition of the Kolmogorov time, and then it can also be written like this. And what you see then is that this ratio here, SL over V eta, that's just Corvalis to the -1/2. Okay, and the Corvalis number is what we're interested in. Okay, now if we look at the thin reaction zones regime, in that regime the Corvalis number is larger than 1. Okay, which means that in that regime V eta is larger than SL, And what that means is that this term here actually becomes small. So in the limit, where you go to a very large Corvalis number, you see that this here becomes very, very small. Okay? So in the thin reaction zones regime, you see from this analysis that this propagation term actually becomes small, and the curvature term is the most important term. Okay? This is now the dominant propagation term in that regime. Okay? That's interesting because, because the SL, which we think is think of as the mechanism for flame propagation, that all of a sudden is not important anymore in that regime. Okay, so we have this here. Now in the other regime, looking for, so that was the reaction regime. Oh yeah, corrugated flamelet regime. Of course, the Corvalis number now is, let's say, much smaller than 1, which means that this will be much larger than 1. And so this term here now becomes very large compared to this, which means that in that regime, this term is not important. Okay? So what we find then is if we go back, let's say, to these two equations, in the corrugated flamelet regime, this curvature term was not all that large. If we assume that dl divided by d is not the same, but that this is order 1. Okay, and this term here, that's really important. Okay, and this term actually is small. Now in the other regime, in the thin reaction zones regime, this term is really important, and this term is small, which means I can use a combined equation, which would be this, to describe both regimes. Okay, and you could even, if you wanted, you could say, okay, if the Corvalis number is larger than 1, then I use d, and if it's smaller than 1, I use dn. Okay, and then you have a term, then you have an equation that in the thin reaction zones regime goes back to, well, this, but even where this first term doesn't even appear because it becomes small. And in the corrugated flamelet regime, this term actually becomes small, and you revert to this. And you see, by doing that, we have neglected the stretch term, but we said that doesn't have a huge effect anyways. Okay? And it could actually be added here again. You could add this term again. However, so if you would just add this term here, then you would see that this term also would remain in the thin reaction zones regime, and you don't want that because it's not in this equation the way the equation is written. Okay? But you could add it and say, make a Corvalis number dependence. Okay, so that is then, let's see if we have that equation here. Yeah, we could write the equation here like this, where now the only difference here is we replace the SLS. The SLS term, that was not important anyways. Okay, when this propagation velocity, when that was SLS, that term was small compared to curvature. So we replace this here. We use this term here from the corrugated flamelet regime, and we use this term then from the thin reaction zone. And then the only other difference here is this notation is introduced, where we say, let me go back, where you have this gradient magnitude, and this is called sigma. Turns out this gradient magnitude, physically interpreted, is the so-called flame surface area ratio. Remember earlier we had a quantity that was called sigma. And sigma is this. You have a volume, and in that volume you have a flame surface. And then sigma would be the flame surface divided by that volume. And sigma, the flame surface area ratio, that would be the flame surface divided by the let's say the average flame surface. Okay, so if I average this, if I find a mean flame front position, it would be something like this. So the average between the ratio between actual turbulent flame surface and that of an average flame front, that's the sigma. Okay, and that makes sense. Remember, because we said that the propagation or the mass burning rate, that is proportional to the to that instantaneous flame surface times the burning velocity. So in a sense, what you see here is the mass burning rate ratio of the instantaneous to the turbulent flame front. Okay? Let's see. Okay, so we have that equation now, and but that equation that's is derived to describe the instantaneous flame front. And now we want to derive equations for kind of a Reynolds averaged equations. Now, one issue when we want to do that, when we wanted to derive Reynolds average equation for the temperature, let's say, we just took the temperature equation. We introduced the Reynolds decomposition. T is equal to T mean plus T prime. And we introduced that in the equation, and then we averaged the equation. And a lot of, and we didn't actually do this, but there are a lot of terms that drop out, because they're an average of a fluctuating quantity. And then the nonlinear terms, they give you these flux terms, like the convection term, that gives you a scalar flux term, and so on. And the reaction rate, that was kind of average. And that's fine. That's that's a good procedure you can do. Here, there's a problem though with that procedure. And anyone knows what that problem is? Anyone can guess?
Is it because G is only defined at the flame surface and not anywhere else? So what do you, when you talk about averaging G, what do you?
Right. So you're absolutely right. I would express it a little differently. It's not that it's not defined anywhere else, but the definition is arbitrary. Okay? I can define it as a distance function, as a hyperbolic tangent profile, and different people do different things. And now, imagine I have a flame front like this, and I define it as a distance function, or I define it as a hyperbolic tangent, or I define it as something else. Then I average this field, and I get a different mean flame front position, right? And so there's some arbitrariness to this, and mathematically, it's a little bit on shaky ground. Okay? And we have developed methods for how to do the averaging. Here, we want to keep life simple. We want to ignore this non-uniqueness for now, and just do it this way. And then, if one is careful, the resulting equations are the same. But keep in mind that there is an issue. So we will ignore this non-uniqueness, and then what we can do is we can take that flame surface, and we can start doing statistics with this. Actually, this here is something that one can still do. Let's say we have a configuration here that looks like this. You have a tube, but there's a flow. It goes here from left to right. This is unburned, and then here we have a flame, and because it's a turbulent pipe flow here, we have a turbulent flame, and that flame that burns that in this direction. Okay, and now I take a camera, and it's a two-dimensional pipe, of course, and then I take a camera, and I just take pictures of this. And then you will see I get, a lot of different realizations, looks this and that. And then I can write down the PDF. So this here is X. I can write down the PDF of where I will see the flame. Okay. So the P of X that you see here, that's actually the probability of the flame position. Okay. So it's just a PDF of a position. And this shows this here. It's called here G prime, but it doesn't matter. It's the same thing. So what you see here is there's let's say a mean flame location. And, there's a lot of probability of finding or probability density in this case. This is the PDF. There's a lot of probability density of finding the flame around its mean. And then, there is something like a Gaussian distribution here. This is from an experiment that was actually done in a transparent spark ignition engine. So this is a real engine experiment. And you see the flame position in this experiment is about Gaussian. Okay? So no probability of finding the flame far away, from the mean, either, to the left or to the right. Another thing you see here is something we have discussed before. I mentioned this first, and then we just looked at a picture of an experimental image, and we also thought we saw this. But here also, you see that now this PDF is skewed. Okay, and that is the same thing as what we said earlier, that you get different curvatures towards the burn than the unburn. Okay, where you have the very high curvatures, there you will have a smaller probability of finding the flame. Because as soon as the flame goes there, it turns right back and goes on the other side of the mean. And where you have the small curvatures, take a long time to fold back. And that's what you see here. So there's a higher probability here to find, let's say, well, you see, of course, that the probability here left and right is the same, and that you just have a skewness. So there's a high probability of finding small perturbations into the unburned and finding large perturbations into the burn. Okay, so that's that PDF, and here we see this again, and it's discussed here again, but we have discussed this before, and so we can skip this here. Okay, and that PDF should satisfy normalization condition, so we can define it like this, and then the P of X from this relation then, because the PDF, from this relation then you can find the mean flame front position. So if I take that PDF now, kind of looks like this then. And, I do this integration, I find 1x, and that would be the mean, the flame front position, or the mean flame front position, that's what we should call it. Now this actually is the right way of doing it. I said earlier, if you take the G equation and you average over this, that's not good necessarily, but here, we haven't used the G equation. We haven't used anything that is not defined. We have only used the position of the flame front, okay, to define a mean flame front position. We just took many of these instantaneous fronts, and we took the mean position of that. Okay, so far we haven't really gotten into this problem. Now, if you take this PDF, turns out you can define a mean, but you can also define a departure from the mean. That would be a variance here. And so that PDF has two different pieces of information and even more. It has the mean flame position, and it also has the so-called flame brush thickness. And what's the flame brush thickness? If you look at this, so if I take many images here, and then I average these positions, then what you would see is that the mean would be something like this. Right? You would get a Bunsen cone. That's kind of what you see also when you look at it. Okay? So you would get something like this, and then you see this here. This would be these departures. And so if I define a length scale from this, you could say, so the flame brush thickness is that's the length scale of these departures away from the front. Okay, that's what we call the flame brush thickness. Flame brush thickness has nothing to do with the instantaneous front. Let's say the instantaneous flame could still be very, very thin, but if the flame goes like this, then it it makes a people have termed a flame brush. Okay. So these are two, and you see that for now, if I want the mean temperature distribution, for example, then you see both of these are very important. The mean is very important, but also the flame brush thickness, because if the mean is here, the temperature doesn't go from unburned to burned right over the mean. You see here the temperature goes slowly, gets, on average, slowly gets hotter, 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 and then some place here is where the maximum temperature then would be. Okay, this here we should skip. And so then we can derive equations for the mean and the variance and of G that then also describe the mean flame position and the flame brush thickness. Did you have a question? Did I use what? Yeah, zero. Yeah.
Zero. So it sounds like a non-dimensional variable. It doesn't have this calculated. So when you take the figure, you take it like from -1 to 1. And from kind of this defines also your variance, and then you define it as flame thickness, as a flame brush.
You mean here?
Yeah.
No, but this is not G, right? X is just, that's a physical length.
Also it's physical.
Yeah, yeah, yeah. Where's the -1 to 1? You mean this here? This here, that's what I said earlier. You shouldn't look at this as a G prime, is what it says here. Look at this as an X. G prime here is just if now you define G as a distance function. Okay, then this would be, then it is always the closest distance to the flame, and it is a physical length. But here we just, and that's how this thing was constructed. We want to just look at some flame position.
If we somehow thought of G as a distance, if you illustrate using this example, how it would be mounted outside the flame?
Yeah. Okay. So I could say, let's have a flame that sits right here, okay? And now I define its G field in 1D. And that G field now has to be 0 right at this point, okay? And then I say it's negative on one side. So, this should be negative, and it's positive on the other side, okay? So what I'm plotting then here is G as function of X, just in one dimension. Okay? So if I say it's a distance function, then it looks like this. Right? That's that's a distance function. It's 0 right where the flame sits, negative on one side, positive on the other side. Okay. Now let's say I take this field and I take the average, the volumetric average. So I take a set here around this, and I take the volumetric average, and I just get exactly this point back. Okay? It worked. Okay? Now, I want to look at a different example. I want to say, I want this to be X on the unburned side. Okay? So I get this again. But I want it to be x divided by 2 on the burned side. Okay? And then it looks like this. Okay? There's nothing wrong with it. You know, I just have to have a kind of a unique definition that doesn't go like this. Okay? I can define the level set like this because you see, it's still 0 here at this point, and it defines me where the front sits. And if I solve this equation, it will, you know, after a little bit, you know, it would show me maybe, let's say the flame moves here to the left, and then the flame would sit here. Okay, so this works perfectly. However, now you see if I do a volumetric average, then the mean would be somewhere here. Okay, it would not be in the same position anymore. So depending on how I define this thing, if I take a volumetric average, it might look different.
So then the issue is that on either side of the point where it is, i.e. the flame will define anything you want as long as nothing is functional.
Say it again? Yeah. No. Well, there are certain regularizing issues. The field has to be regular. That's the point. You see, because all this equation says is, you see, the equation says at one point, dg dt, let's say there's no convection speed, okay, is equal to the gradient times Sl, okay? So you see that at this point here, you know, this will be a little larger, and at this point it will be a little larger, at this point it will be a little larger, and it would tell me this thing moved here. But for that, the gradient has to be regular. And as long as it's regular, it doesn't go up and down, it doesn't have singularities. If this has singularities, then you're in trouble. And as a matter of fact, if you just let this thing go, it usually develops singularity. So that's why one always has to do this reinitialization.
That leads to my next question, where you say you could have G equal X on the main side, G equal half X on the other side, and get a discontinuity at the origin. So that would make it
That would make it difficult to, well, then you would have to use upwinding schemes that know the propagation goes in this direction, and then you have to use the gradient in that direction. But of course, this is an example that no one would ever use who is right in their mind. But it was just an illustration here. But see, this could be continuous. And that's not, you know, so far out of the possibility. See, could be this, okay? But the main point here is that you could still think, I mean, you know, I define something and I stick with it, and that's it. And that's good for solving this equation, and that works perfect. You know, there's nothing wrong. This doesn't have to be a distance function. As long as, the only reason why we do the reinitialization, always bring back to distance function, is because the field becomes irregular. You get, it steepens, the gradient steepens up and so on, and then this doesn't work anymore. And so this method is very accurate. Why is it accurate? Because you're not trying to advance a discontinuity. You're trying to advance an equation for a field that's very, very smooth. Okay, and that's why it's accurate. Now, if this field steepens up and becomes a discontinuity, actually, mathematically, there's nothing wrong with this until it is a discontinuity. But you know, it becomes less accurate to solve. Now, coming back to this averaging issue, you could say, oh, I just choose something and I stick with it. And that's, let's say, that's fine. The problem is, mathematically it's bad. Because if you have an arbitrary definition, the average equation, that should not know necessarily how you defined your instantaneous field. And the average equation can't be arbitrary. You know, it has to define, if you say this is my mean flame position, then it has to have a very clear definition. And that's the problem. I mean, you can mathematically show actually that it's not a good idea to do this because you violate some symmetries of the equation by doing this and so on. But that probably goes too far. Okay? I always run back and forth because I think it's very hard to see what's up there. And then I think maybe it's better over there. And then I go over here and I look again and I think, oh no, maybe it's better over there. And I keep doing this now for 5 days. So, I go up here. Good, so we keep in mind this is mathematically not the best way to do it, but is easy to understand. And it leads to the same equation, so that's why we do this. You just take the equation that we had earlier, and we introduce these mean and fluctuation, Reynolds decomposition, and then we average this equation. And then what you see is that there's a term here like this, SL naught times sigma, and the mean of that. Okay? And that's a term that needs to be modeled. And then this term here, we neglected this anyways. You also get a term here, which is the sigma times the curvature mean, and we need to model this also. And so the curvature term, that is something like a diffusion term we said yesterday. And so we model it like diffusion. So rather than d times kappa times this gradient mean, we write a dt, a turbulent diffusivity, times the mean curvature times the gradient here of the mean G field. And then this here, so that's the model for this. And that's very much like we would model a diffusion term. This is a term that we don't usually have, but thinking about it now, we can also understand what this means. So we said earlier, sigma times SL. Sigma is something like a measure for the actual local flame surface times SL, so this is kind of the mass burning rate. And so the idea here is we replace this by the mean. This should actually have a mean here, tilde on top of it, by the gradient of the mean field, and multiply this now with what we call a turbulent burning velocity. So the mean field now, that gives you a lot less curvature, which means that SL, or the ST, the burning speed that is in front of it, that has to be much larger. Okay? So what's important about this then, so the question is, well, how do you come up with this? And the answer is, if you look at the final model equation, it's this. And one thing that's very important here, let me see if this is mentioned here somewhere. Yeah. So this is the equation. And you see that the equation, it looks very similar again to the instantaneous equation. You see in the instantaneous equation we had rho SL sigma, or sigma is the gradient of the instantaneous field, or the magnitude of the gradient. And here we have a rho ST and then the gradient of the mean field. Okay, and here we have, and here also this is very similar. So typically, in turbulence modeling, what you have is always something like this. Here you have the kappa value is large in the instantaneous field. The curvature is large, but this diffusion coefficient is small. And in the average equation, the curvature of the mean field is small, and the diffusion coefficient then is large. Okay? And that's the same, if the models for the Reynolds stress and so on. That's very typical way of modeling. And here's the same. You see, sigma is large, SL is small, and here this is also sigma mean is small, but the coefficient now is large. And so, and we still don't know what that coefficient is. But why do we do modeling like this? Very often we do modeling like this. Why do we do modeling like this? Because it preserves the mathematical properties of the original equation. Okay? Turns out in modeling, one thing is always very important, is that your modeled equation has the same mathematical properties as the original equation. Why is that? You know, there's a big theory behind it. You can show that certain equations have certain symmetries. And models for these equations then always have to have the same symmetries. Okay? So one equation might be Galilean invariant, or might be invariant under translation in time or in space, or you know, certain transformations. And then the model equation also needs to have the exact same invariance. Okay? And so that's why modeling is often done like this. This is, you know, just a good example for that. And you could say that when we derived this equation, it wasn't actually right the way we did it, let's say, because, you know, I said we shouldn't actually average the filtered field. But by choosing the models for these individual terms then, because we did it such that the original mathematical properties, you know, are there again, you know, we corrected for that mistake. Okay, so that's why we do this. Turbulent diffusivity, we know how to compute the turbulent diffusivity. We have done that for other quantities now also, so that's not so hard. And then this last term here is closed. And then here we have the turbulent burning velocity, and the turbulent burning velocity at this point, we don't know what it is. So that's a quantity that we still need to model. And otherwise, we have a closed equation. And then you saw earlier that the temperature, what do we want to know from this? The only reason why we solve this is because we want to solve, let's say, the momentum equations. And the momentum equation, you need the density. And it's, of course, very strongly modified by the combustion process. Right? Rocket wouldn't fly if it wasn't for the density change that you get due to combustion. And so the density change, let's say, that's similar to the temperature change. And that we saw earlier, if you know the mean position and you know the kind of the variance around it, then you can, you know, determine somehow the temperature. And so that's why here also there is a variance equation that gives you a measure here for the flame brush thickness. Okay, so G prime now, that is a measure for the flame brush thickness. And you see this has a production term here and a dissipation term. This is very, very similar here to the equation for the mean, for the mixture fraction variance, for example, or temperature variance. Except that this diffusion, what looks like a diffusion term, is a little special. Okay. Okay, so the only thing we need to model still then is this turbulent burning velocity. Any questions about this?
Actually, the ones you solved is the values in the Reynolds.
Yeah.
I haven't done all the maths. I haven't done the maths at all, but just thinking of how we derive like the Reynolds equations from the number slopes, I would expect to have a term like U flux, G flux, kind of. Like, is there any hidden assumption in the first, like the second term of the first equation?
Here you mean a scalar flux?
Yeah.
For this?
Yeah, from there, the fluxes. Is it like a hidden assumption that these are kind of uncorrelated, or is there...
No, actually, that is a really good. That's a really good question. That's why I said earlier, you know, by choosing the right models, you correct for that error. Essentially, what you will have here is this. You have this. You do your, you know, and then you should get a flux term. And then the question is, how do you model that flux term?
Which is like
Now, let me go a step back. If I introduce the Reynolds decomposition in here, what I get is a term that goes with the molecular diffusivity, and it does not, like a dissipation term, have a gradient squared. So that term usually goes away. Okay? So that's very similar to when you take the Navier-Stokes equation, momentum equation. and you do the Reynolds decomposition, then what was originally the diffusion term, that usually goes away. Okay? And then you get the flux term, and you model that like a diffusion term. Okay? Here's the same thing. This goes away, and here you get a flux term. And now comes the trick. Now we know, now we would say, let's model this like a diffusion term. Okay? But then you would probably think about it twice and think, hold on. The original equation did not have a diffusion term. The original equation only had a curvature term. So if I model this like a diffusion term, I change the mathematical characteristics, the mathematical properties of that equation. And that's why you would say, let's take this and model it as a turbulent curvature term. Okay? And so this is how, well, this is a really good point. This is how this term comes in the first place. And again, this is how we correct, basically by knowing how modeling has to be done, how we correct for this mistake of averaging the arbitrary.
And the second question is, now we know the front plane, but essentially what we want to solve in this case is how to here we solve for species.
Yeah.
Or when you do a practical calculation.
Yeah. So really what you want is two things. You don't want the species. You couldn't care less about the species. What do you care where you have, CH or H2O? What you want is, as I said, the density, because you need that to close the problem. And then you want emissions. So things like CO and NO and things like that you want. Okay? And so the first one you get by that is similar. Maybe this comes later in this part. Maybe not. But what you do essentially is this: you know the distribution, let's say, of flame front. You know how much flame front you locally have on average, or you know PDF. Okay, and then you take this G and you solve premixed flamelet equations. Okay, and these premixed flamelet equations, they tell you the species as function of G. Okay. Okay.
So you're getting your flamelet tables, you use species as function of Prof variable and J.
Yes. And then you have here you have the field of G, which means you can map one into the other. Now for NO, NO because NO is such a slowly evolving scalar, we usually solve separate equations. We solve a separate equation for NO that has a source term, and that needs to be provided. And that is provided in a very similar way. You go in your flamelet table and you look at what's the source term for NO, as function of G, and you map it into the G field. Yeah.
Because since you want the NO, since it's slower kinetics, can you kind of decouple how NO species?
You can often do that, although I think modern combustion devices they go to so extreme, let's say low temperature conditions, that it's not only thermal NO, that it's also prompt and especially N2O. The NO formation becomes important. And for these, it doesn't couple back to the heat release, so you can always do that post-processing. But it's a little more complicated to do that as compared to thermal NOs.
Your emissions are a function of G, you have to reinitialize G every so often. You just solve your emissions for each time step, then you have to also reinitialize.
Well, you don't reinitialize the... See, all you use from this field is just the location, not the whole field, right? You just use the location. And the reinitialization should not change that location.
Well, but you were saying before that the emissions are a function of G. So you say, all right, my G value is 5, and the last time it was 4, then so much emission will produce. And then if you have to reinitialize at some point, then you went from 5 to back.
Yeah, no, yeah. So this is, let's say, you know, this very roughly, this is what you would do. And say this is your turbulent flame. Now, I don't want to use the values of G away from the flame. I only want to use what that equation tells me is the position where the flame is. Okay? And then, on the other hand, I have solved, you know, my 1D laminar flame, and it kind of looks like this. This would be temperature, and this is T naught. Okay, so I know this is the temperature right here. Okay, this point needs to map right here, and now you see I can map if I know the distance from the flame, and that's the advantage of initializing this as a distance function. Then I can map this as the with the distance to the flame. But that's not using the G field. That's using, you know, a distance to the flame. So essentially, you just map that one point. You map that back into the, you know, to this surface, and the rest, you know, is just the way it evolves. Really, though, we do this a little different, which I didn't include here. Because it's so that's the conceptual idea, but in reality, wondering if I should. I think, you know, we'll just go on now, and when the time is up, the time is up, and it doesn't matter too much. So I might as well tell you how we do this. Okay. See, well, that's what I said earlier. All this equation gives you is where the black line is, and it doesn't tell you anything. Okay. However, and that's good for the corrugated flamelet regime, okay? Because the corrugated flamelet regime, you know, I don't even need to know all this stuff. I just need to know it's burnt here, it's unburnt here, and that, you know, for old days when we did simulations for that regime, that's what we do. We just use basically you get equilibrium concentrations for all your species, except for NO. Okay. So. But now, if you're in the thin reaction zones regime, it's not all just unburned and burned. You have sometimes a distribution here of, you know, a broadened preheat zone. And then the question is, how do you deal with that? And so what we do is this. We solve a progress variable equation in addition to the G. Okay? That progress variable equation, now that needs to be solved as a chemical solution. How do we solve that? We solve it from the solution of the G equation. We say the G equation, that we trust that the G equation can always tell us exactly where this black line is. Okay? And then from that, we take the, we build a source term from that information. We build a source term that we use in the C equation. So the C equation, the progress variable equation, that is now has a source term that always makes it, let's say C naught, the inner layer value of that, follow that black line. Okay? But then the rest of that field, that is now a field equation. It's defined everywhere in the space. That interacts with the turbulence, and that will give us, you know, these fluctuations here of the temperature in the preheat region and so on. Okay. So that's what we do, at least in LES. In RANS, I have to say I never did RANS simulations in my life. No, I did actually. I did, but I haven't for a long time. No, that's not true either. We do actually RANS simulations for internal combustion engines, but not for much more. Okay. Let's see. We talked about this. We talked about this. Oh, we were through with this. Any other questions about this? Yes.
What's the advantage of using the velocity compared to the CFM?
Were you here yesterday? I said it yesterday.
Because of the velocity?
Because I said the CFM, that doesn't have a, that doesn't have any information about the chemistry, okay? Because the SL drops out.
But in this the equation of the there's no information about the premixed.
The what? Sorry, this air conditioning here is so loud. It's really hard to
In this
understand.
picture, the equation of G, there's no information on the premixed as well. We have the turbulent velocity.
Yeah, it's the turbulent burning velocity, right?
It's not the laminar.
Right, but you will see later on that that laminar burning velocity that comes back in through the turbulent burning velocity. That's a part of that. The chemistry affects the turbulent burning velocity. And so that will, come back in the turbulent burning velocity. But I should say, I mean, if you have a CFM or not, the question is a Process variable equation or a Levitt-set equation, okay? And in RANS, I think, in RANS, you could use a Process variable equation. I mean, there's nothing wrong with it. The only issue is, if the question is, how do you model the chemical source term? If you model the chemical source term by having, so you have a Process variable equation that has, that kind of looks like this. E rho C dt plus del dot rho U C plus or minus del dot rho D del C and then minus this m dot I. And so this here, if you model this as sigma times SL, so if you model this with a propagation, if you model it like this, that's fine, but you need to make sure somehow the chemistry is noted by that equation. Okay, but let's say you can do that, and then it's fine. The problem is sometimes people use a real propagation term, and that's wrong. If you use a propagation term, and that propagation term, as we saw, it includes this diffusion term. Okay, so really they write something like a G equation, make this a propagation term, but just for numerical stability, they also add this term, and that is wrong. Okay, because you count this term twice. Now, this is so in RANS you could say the G equation it's just essentially it's a numerical technique. It's a numerical technique to solve that equation, and all the physics and so on that comes through some of the, let's say, the variance equation modeling, and also the modeling of the burning velocity. Now, in LES it's different though, because in LES you cannot solve the C equation just by itself. And the reason for that is, and we made this point many, many times in basically every single paper I write. The problem is this. You remember I had this with this picture with an LES mesh on top of it? If you have an LES mesh here on top of it, which is, let's say this is one point, and this is the next point, and you see that typically, as long as the subfiltered Dampf-Kühler number is larger than 1, the temperature change from fully unburned to fully burnt will happen within 1 cell. Okay? That's just it. If the subfiltered Dampf-Kühler number is larger than 1, it will happen within 1 cell. That means it is a shock. It's like a shock on your mesh. And you need to do something. You cannot solve a diffusion advection equation that has a shock without using special numerical techniques. Okay? People in fluid mechanics, they have spent their life doing nothing else than developing numerical techniques that would accurately capture a shock. Or people who do multi-phase flow, atomization, they spent their life developing numerical techniques that can track an interface. Okay? And it's the same here. It would be naive to say we can just solve a progress variable equation and not worry about this. Okay? And so people do this, but most of them they worry about it. So for example, there is the thickened flame model. Not sure if you have heard of that. The thickened flame model then, you say, okay, I can't solve this because there's shock on the... So what I do is I make, artificially, I make the diffusion much, much faster. So they have a factor in front of the diffusion coefficient, factor of 10 or whatever, makes diffusion much, much faster. So now the flame thickness becomes super thick, okay? But this means, because the burning velocity depends on SL is equal to D divided by the chemical time scale to the 1/2. Right? If I make this 10 times larger, that means I make this 3 times larger. Okay? Now I have the wrong propagation speed. So what they do then is they added another coefficient also to the chemical source term. Okay? Which is now 1/10. So if I put a factor of 10 here, oh no, and also a factor of 10 here, then I get back the same flame speed. Okay? The problem though is that now you moved the regime. You made the chemistry very, very slow, and you made the diffusion very fast. Okay? You know, you have to balance these, which means in the regime diagram, you move to a different regime. Okay? So there are issues with this. It's not simple. And so the G equation, I said this earlier, is a numerical technique. And what we do with it is a numerical technique to solve for an interface, you could say. So that's why I think especially in LES, the level set equation has a lot of advantages. But you could also, if you do solve a C equation, then I think you have to do something like shock capturing or something. You have to do something else. And as I said, we also solve a C equation. We solve an equation like this, but this source term here, we close that from, you know, solving from the solution of diffusion. Yeah. There's always one always has to. There's not always the same answer to these questions when you talk about LES or RANS. It could be very different. In LES, in RANS, I think there's nothing really wrong with solving the equation. Oh, I forgot to hook up my computer today. So, it just goes to sleep. Any other question? Yeah.
So, does G always always a continuous surface? In other words, if there's some kind of isolated thing that's coming off the plate, G capture, and I go back to your picture that you were showing, so there's all of that little thing that's off the continuous surface, the little red blob that you showed. G equation capture that?
Yeah. What's particularly good about level set methods is they can handle topological changes very, very easily. That's why they're used very often also for interfacial flows, because you might have a block coming off, and level set methods. Level set methods actually, I'm not sure if you guys know this, they're used a lot in animation. So if you look at all the movies you see today, you know, if there's any computer graphics in these movies, there's a very good chance it was done with level set methods. So for example, at Stanford we had a guy who worked in computer science, and he was also working on level set methods, Petkow. And so he said he did the cloak of Yoda in the Star Wars movies. That was done with level set. And then I was on a PhD committee of one of the students there. He was doing simulations for the what's that movie again? The Pirates of the Caribbean, the Swirl or whatever. So level set methods are used a lot actually outside of combustion, and which is why there's a lot of really good work on the numerical techniques also for this. So my computer went crashed and I had to restart. And so it's starting up the whole thing here again. Okay, so okay, any other questions about this? Yes.
I have a general question coming back to what you said about the flame theory model. Essentially, all problems in this combustion modeling comes numerically, that your flame is much thinner than your numerical grade. In flame thickness, as you said, they accept this thing and they say, okay, then I thicken my flame and kind of resolve the flame on my numerical grade. In flame surface density plus the level set approaches, we say, okay, it's infinity thin, and we model it with kind of interface. From a practical point of view, however, when you do your numerical simulation, your LES, in a grid, you have this interface. So what is really happening in a grid cell, you have this interface, and you have something burned and something unburned. But all you have in your cell is your filter value. So I'm kind of wondering, like, yes, in reality, you try to model like a delta thing, but all the flow understands back is a kind of mean value, which comes from like, I have my egg in the oven, my feet in the fridge, but on average I'm okay. So how this is balanced numerically?
No, this is
yeah. Diffusion, numerical diffusion, I say. Like you thicken the flame in the grid size.
No. Who thickens the flame in the grid?
By representing a delta function with the mean value, you artificially thicken your flame at least to the grid size numerically, or no?
Yes, but these are things you can, if you want, you can take care of it. It's just like in a finite volume type of setting, you always have different states in one set, and you average over this, but then you need to worry about how this average is constructed. So if you have a mesh like this, and the let's say the G field would tell you this is what it is, that means the flame is here, then the flame is here. Then you have a part unburned and a part burnt in that set. And you can have, that's what we do as a matter of fact, you have a probability of finding burnt, which depends on the value. And so here you would have a 60% probability of finding burnt and 20% or 40% unburnt. And so the density, the mean density you get there is something in between.
But the mean density not calculated from the mean value of the cell.
Well, I mean, it's constructed from the mean value of the set. See, the instantaneous solution here of the temperature, let's say kind of looks like this, which means that here I have so many percent unburned and so many percent burned. So I can construct these. I can reconstruct what I have on the subgrid subgrid scale. Maybe we should discuss this later. So what's the break situation? Today is 10:15, right? Today we do the normal half hour. Okay. Good. So let's move on, and I appreciate actually the discussion. It shows that you guys are, thinking, but also listening to some extent. That's good. I appreciate that. So what we said earlier, the turbulent burning velocity, that's the one quantity we're still missing. And again, there's a whole theory that makes that comes up with complicated stuff. And I want to skip that, and I just want to give you the essence of how one thinks about this. And so let me see. So there's a famous theory here, and it's not from yesterday. It's from the day before, from Dammköhler, and it's quite old. And he thought about this problem, and you will see that all the stuff I was telling you here about this regime and that regime, that's fairly recent. You know, this is stuff from the last 10 years or 15 years, or let's say, I think it's recent, but maybe it is not so. I mean, let's say 15 years. But if you look at what Dampköhler already, you know, his thoughts in the 40s here, or 1940, it was very similar. And that's very interesting. So Dampköhler said he identified two different regimes. And he called one the large-scale turbulence regime, and he called the other one the small-scale turbulence regime. And you see already that this is similar, has some similarity here with what we call the corrugated regime, where we say the turbulence scales are large compared to the flame scales, and the thin reaction zones regime, where we say the turbulence scales are small compared to the flame scales. Okay, and this is how he thought about it. He said, okay, let's take the it's, you know, think of a pipe flow like this, or, you know, let's think of a pipe flow like this. And then I have a flow that comes here from left to right, and, you know, it's turbulent. And then here, I have a turbulent flame, and that turbulent flame, it goes from right to left, okay? So, and he said, so what's the mass burning rate here of this? And he said, mass burning rate, of course, and that's what we said before. That's easy to see. The mass burning rate is rho unburned times the surface area of this flame times Sn. Okay? That's the mass burning rate of the instantaneous flame. And then he said, well, let's see, if I just want to look at a mean flame, the mean flame position here is this here. Okay? A flat flame, that's the model now. Then this has to burn faster, but the mass burning rate of this here, that would be just rho unburned times this area here times a modified speed, okay? And you see immediately that AT is larger than A, which means now that ST has to be larger than Sn, okay? Okay, so that's kind of the definition now of the turbulent burning velocity, or that's how it's introduced. And the question then is, so, you know, the rho u is the same, so what follows from this is that ST over SL is equal to AT over A. Is the area ratio of these two. I don't want to go in these little details here, but then the question is, what is AT over A? And he thought, well, let's see what happens if I have a Bunsen flame. You have a nozzle here, and then, you know, you have a flow that comes out of the nozzle, and then here you have a flame that sits here like this, right? And he said, so what's the mass burning rate here again? The mass burning rate here is you know, rho u times rho u times SL times A, and so if I look at just the mass flow rate that comes down here, that would be u times rho unburned again times this. So this here would be a flame, and this here would be the cross section, you know, of this burner. Let's call this A. Okay. And so what he realized was that, so what is this flame surface here? What's the flame surface with respect to the inlet velocity? Okay? When you change the inlet velocity, SL doesn't change. Okay? Rho u, I can cancel this out. Cancel rho u out. SL doesn't change, so I could say AF over A is equal, so this here, sorry for squeezing this in here, but AF over A is then U divided by SL. Okay? And so what you see here, the more you increase U, the larger this flame surface will be. Okay? So he says the flame surface that depends on the velocity. And so the velocity you have here, that's the velocity fluctuation. That creates, in this case, the flame surface. For the Bunsen burner, it's the inlet velocity that creates the flame surface. Here for the turbulent flame is the velocity fluctuation. So his model, and that is that's the main part here. You know, that first part we had here, that was just mass conservation. That's trivial. But this is the actual model. Okay, it comes from just looking at a Bunsen burner. Now, if I plug this in here, let's say ST over Z is equal to AT over T, and I plug this in, then you see ST is just proportional to V prime. Okay? So does that make sense? So what this says here is that propagation velocity, it does not depend on the laminar burning velocity or the flame thickness or any kinetic parameter. Does that make sense? It makes sense in a way that the flame now, in that limit where you say is a large-scale limit, the flame is infinitely thin, which means that, you know, you don't really see what the flame is. And the idea behind this now, or not the idea, but the resulting fact behind this is that you always have, you know, look at this, for example. You have turbulence that creates these fluctuations, and it is then the burning velocity that just takes them out. But how fast or how slow the burning velocity takes these out, that doesn't matter anymore. Because as long as I have created that much surface, that surface will be eaten up by the burning velocity eventually. It doesn't matter how fast or how slow. That's a little similar to, you know, in turbulence, where the turbulent flow doesn't depend. I said this earlier. For large-scale Reynolds number, for a large Reynolds number, the turbulent flow doesn't depend on the Reynolds number anymore. Okay. What does that mean? If you have a turbulent flow, it looks like whatever. It creates some mixing, and making the Reynolds number larger. That essentially means make the viscosity smaller. So you make the viscosity smaller, and nothing happens. The only thing that happens is the dissipation now takes place at even smaller scales. Okay, but it doesn't change the large scales of the flow, and that's the same. That's the same here. Okay. Now for the small scale turbulence, he correctly realizes now there must be an interaction of the flame with the turbulence. Now, if you look at a flame, and if you look at what is the propagation speed of a flame, it is square, you know, scaling arguments. It's square root of d over dc. Okay. So he said, well, if I have turbulence now mixing in the flame, then definitely the diffusivity, the transport, that will be faster. Okay, and he said maybe the turbulent time, the chemical time scale, you know, that just depends on chemistry. That should not be influenced by the flow. That's just just chemistry. And so what he said was, for the turbulent burning velocity, it scales in a similar way. It's the interaction of transport with chemistry, but now it's turbulent transport that interacts with the chemistry, and not laminar transport. Okay? And if you bring these two together now, then you see the TC cancels out. So ST over SL then is just equal to square root of DT over D. Okay, so this is the relation here as I showed it, and then if you divide this by this, then you see ST over SL. That goes like DT over T, DT over D. Okay. Okay, so DT now, that can be written as, we said that's the same as, turbulent Schmidt number equal to 1. That would be, turbulent diffusivity would be the same as the turbulent eddy viscosity. We said for the eddy viscosity, we can say eddy viscosity is proportional to V prime times Z. So you see I replace this by V prime times Z. And then the D, I can write this as SL times LF. You know, we don't have this on the board, but we can, you know, just scaling arguments. And then you see, interestingly, we get back these V prime over SL and L over LF. And this here now actually is the turbulent Reynolds number. Okay. So now we have these two regimes: the large-scale regime where ST is proportional to V prime, and the small-scale regime where ST over SL is, you know, this. And what's interesting now is, and that's what I said earlier, this is where SL comes back into the picture. Okay, so in that sense, we can interpret this this model that we looked at yesterday, that was based on the flame surface density and so on. We can take that model and interpret it as a model that should be valid only for the corrugated flammable regime, or for, let's say, what Dampköhler calls the large-scale turbulence regime, not for the small-scale. Okay, so there have been a lot of measurements of ST in the past, and people always try to correlate it back into expressions like this. But if you look at it, so this, what's this expression? This expression says ST is equal to SL plus, and then, you know, SL times, you know, whatever this is. And what's interesting is, though, that this is not the same as this, because here you see I have a length scale ratio. And here, there's no length scale ratio. Okay? So this is an expression like this. So people have always tried to, you know, correlate the data back to expressions like this, but you see that this does not depend on the length scale ratio. The turbulent length scale doesn't appear. And you see, if it matters, if, you know, Dampköhler was right, then there should be this parameter L over LF that should matter for the you know, for this quantity, which means with a quantity like, with an expression like this, you cannot express the you know, ST, or yeah, you cannot express ST right, and you cannot you know, match all the experimental data. So now this here shows a comparison with experiment. This is ST over SL as function of the V prime over SL. And you see there's a huge scatter here in the different data, which might show you either that it's very, very hard to measure this quantity, or even to define this quantity right, and that's why you get the scatter, or that this ST cannot be expressed as a sole function here of V prime. Okay? Shows you one of these. Okay, so this is Dampköhler's theory, and you see here, this is the small scale, small V prime here, so that here in this regime ST is proportional to V prime. And you see the data kind of shows this also. And then here there's this bending off. This has always been called the bending of the turbulent burning velocity. And this just shows that you know, it goes differently here in this regime. When we look later on, we look at other data. Okay, so let's break here, and then afterwards we talk shortly about a little more elaborate model, and then also we want to talk briefly about turbulent diffusion.